In this video, I am going to present the details about election algorithms and transaction models. Election algorithms are meant for electing a coordinating process from among the currently running processes in such a manner that any instant of time, there is a single coordinator for all processes in the system. Election algorithms are based on following assumptions. Number one, each process in system has unique priority number. Number two, whenever an election is held, process having highest priority, no number among the currently running processes is elected as coordinator. Number three, on recovery, a failed process can take appropriate actions to rejoin the set of active process. So two different types of election algorithms are there. One is Bully algorithm, number two, ring algorithm. Bully algorithm, and this was proposed by Garcia Molina in 1982. In this algorithm, it is assumed that every process knows the priority number of every other process in the system. When a process sends a request message to coordinator and does not receive a reply within a fixed timeout period, it assumes that coordinator has failed. It initiates election by sending an election message to every process with a higher priority number than itself. If PI does not receive response in timeout, means it has highest priority. It will become coordinator and will inform all processes through message. If PI receives reply, means other process with higher priority are available and does not take any decision and waits for message of coordinator. When process PI receives an election message, it informs sender that is alive and now PJ will do election and will become coordinator if it has highest priority number. Otherwise, the PJ will initiate message and this will continue. So this is shown in the diagram. In this diagram, we can see an example of how the Bully algorithm is working. The group consists of 8 processes numbered from 0 to 7. Previously, process 7 was a coordinator, but it has just crashed. Process 4 is the first one to notice this. So it sends election message to all processes higher than it, namely 5, 6, and 7. It is shown in the diagram. Processes 5, 6 both respond with OK. It is shown in the diagram and the diagram B. Upon getting the first of these responses, 4 knows that its job is over. It knows that one of these bigwigs will take over and become coordinator. It just sits back and waits to see who is the winner. Winner will be, and it can make a pretty good guess. So the ring algorithm, it processes are arranged in logical ring. Every process in the system knows a structure of ring. If successor of sender process is down, it can be skipped until active number is achieved. When PA requests coordinator and it is down, it will wait for timeout. It initiates election by sending election message to successor. Message contains priority number of process PA. Each successor will add its priority number on receipt. It will circulate and reaches PA. Ring algorithm. And this is another election algorithm based on the use of a ring, but without a token. We can assume that the processes are physically or logically ordered so that each process knows who its successor is. When any process notices that the coordinator is not functioning, it builds an election message containing its own process number and sends the message to its successor. If the successor is down, then the sender skips over the successor and goes to the next member along the ring, or the one after that until a running process is located. At each step, the sender adds its own process number to the list in the message. Finally, the message gets back to the process that started it all. That process recognizes this event when it receives an incoming message containing its own process number. At that point, the message type is changed to coordinator and circulated once again, this time to inform everyone else who is the coordinator and circulated once again. This time to inform everyone else the coordinator is and who is the members of the new ring is. When this message is circulated once, it is removed and everyone will go back to the work. The discussion of two election algorithms, the Bully algorithm and ring algorithm. Bully algorithm, when lowest priority number process detects coordinator failures in a system of n processes, n minus 2 elections are performed, leaving a failed coordinator unsender. In worst case complexity is the O of n squared. The best case is n2 messages, n minus 2 messages are required. The complexity is O of n. A ring algorithm, election requires 2 into n minus 1 messages are required. N minus 1 messages for one round rotation of election message. N minus 1 messages for one round rotation of coordinator. Atomic transaction. An atomic transaction is an indivisible and irreducible series of database operations such that either all occurs or nothing occurs. A guarantee of atomicity prevents updates to the database occurring only partially, which can cause greater problems than rejecting the whole series outright. There is an example is given. Now look at a banking application that updates an online database in play. The customer calls up the bank using a personal computer with a modem with the intention of withdrawing money from one account and depositing it in another. The operations are performed in two steps. One is the withdrawing operation. The second one is the depositing operation. If the telephone connection is broken after the first one, but before the second one, the first account will have been debited, but the second one will not have been credited. The money vanishes into the thin air. So transaction model. Various types of storage media are distinguished by their relative speed, capacity, and resilience to failure. The first one, volatile storage and non-volatile storage and stable storage. Transaction processing system. Operations on a database are usually carried out in a form of transactions. Programming using transactions require special primitives that must either be supplied by the underlying distributed system or by the language runtime system. Transaction primitives. Programming using transaction requires special primitives that must either be supplied by the operating system or by the language runtime. Examples are begin transaction, end transaction, abort transaction, read and write. Nested transaction. The top level transaction may fork off children that run in parallel with one another on different machines to gain simplify the programming. Each of these children may also execute one or more subtransactions or fork off its own children and provide a natural way of distributing a transaction across multiple machines. Follow a logical division of the work of the original transaction. For example, a transaction for planning a trip by which 3 different flights need to be reserved can be logically split up into 3 sub-transactions. Each of these transactions can be managed separately and independent of the other 2. Acid properties. The characteristic feature of a transaction is either all of these operations are executed or none are executed. This all or nothing property of transaction is one of the 4 characteristic properties the transaction have. One is atomic, second consistent, third isolated, and durable. The properties of transactions. Transactions have 4 properties. One is atomic, consistent, isolated, and durable. These properties are often referred to by their initial letters called ACID. Write ahead log. Write ahead logging, called as intention list. The changes are first recorded in the log, which must be returned to stable storage before the changes are returned to the database. In a system using WAL, write ahead log, all modifications are returned to a log before they are applied. Usually both redo and undo information is stored in the log. Write ahead log. So in this diagram, it gives an example of how the log works. We have a simple transaction that uses 2 shared variables, x and y, both initialized to 0. For each of the 3 statements inside the transaction, a log record is written before executing the sequence, giving the old and new values separated by a class. If the transaction succeeds and is committed, a commit record is written to the log. but the data structures do not have to be changed as they have already been updated. If the transaction abort, the lock can be used to back up to the original state. Starting at the end and going backward, each log record is read and the change described in it undone. This action is called rollback. Commit protocols. Commit protocols are used to ensure atomicity across the sites. A transaction which executes at multiple sites must either be committed at all the site or aborted at all the sites. It is not acceptable to have a transaction committed at one site and aborted at another. Two-phase commit protocol is widely used. Two-phase commit protocol assumes file stop model. Failed sites simply stop working and do not cause any other harm, such as sending incorrect messages to other sites. Execution of the protocol is initiated by the coordinator after the last step of the transaction has been reached. The protocol involves all the local sites at which the transaction executed. Let T be a transaction initiated at site SI, and let the transaction coordinator at SJ and be CA. Obtaining a decision. Coordinator asks all the participants to prepare commit transaction. Upon receiving the message, transaction manager at site determines if it can commit the transaction. Phase 2, recording the decision. Transaction T can be committed to CA, received by a ready T message from all the participating sites, otherwise C must be aborted. Coordinator adds a decision that commit T or abort T to the log and forces the record onto a stable storage. Once the record stable storage, it is irrevocable. Then coordinators send a message to each participant informing it of the decision. Participants take appropriate action locally. Handling the failure, site failure. When site SI recovers, it examines its logs to determine the fate of transaction active at the time of the failure. The protocol we can look at is called the two-phase commit protocol. It was introduced in 1978 by Gray. Although it is not the only such a protocol, it is probably the most widely used. The basic idea is explained in this diagram. One of the processes involved functions as a coordinator. Usually this is the one executing the transaction. The commit protocol begins when the coordinator writes a log entry saying that it is starting the commit protocol, followed by sending each of the other processes involved a message telling them to separate commit. The concurrency control, first one locking, then optimistic concurrency control, then timestamps. Concurrency control locking, the oldest and most widely used algorithm. A process before read and write requires the scheduler to grant a lock. Upon finishing the read or write, the lock is released. In order to ensure the serialized transaction, two-phase locking protocol is used. Two-phase locking, in the first phase of the transaction, new locks only appear, and in the second phase, locks are released. As the transaction is not allowed to acquire any lock once it has released any one lock. Concurrency control locking. Acquiring and releasing locks precisely at the moment they are needed or no longer needed can lead to inconsistency and deadlock. Instead, most transactions that are implemented by locking use what is called a two-phase locking. In two-phase locking, which is shown in the diagram, the process first acquires all lock it needs during the growing phase, then releases them during the shrinking phase. If the process refrains from updating any files until it reaches the shrinking phase, a failure to acquire some lock can be dealt with simply by releasing all locks, waiting a little while, and starting all over. Further, it can be proven that if all transactions use two-phase locking, all schedules formed by interleaving them are serializable. This is why two-phase locking is widely used.